Chapter 6 title is Torque and Equilibrium. So we are going to start a new concept because now we cannot no more treat things as a particle. It has a size. So it can spin, rotate, and we have to take that into account. So the rotational motion requires something called torque. Force is not sufficient to describe rotational motion. So with that, we come to redefine the equilibrium. So that's why the equilibrium is there. This chapter content, we'll start with describing this extended object and where the force is applied on this extended object matters now because we cannot reduce them to a point. So it has a size. So where the force is applied is of significance. Then we define this quantity called torque, T-O-R-Q-U-E. Number 3, then we will revisit this equilibrium for a rigid object. So we're going to need an additional condition for mechanical equilibrium. Number 4, we will go to some physiological application where we see that classes of levers which comes in this mechanics applied to physiology. Number 5 and 6 we will skip. Okay, so it's going to be a short chapter. Right, now look at this figure. In the left side, we have some irregularly shaped object, and we apply 3 forces, F1, F2, and F3. And we know it is given to us when you add these 3 forces that the net force is equal to 0, right? That is given to us. In A, that object will be in equilibrium. Good. We apply the same 3 forces here. Maybe the same object or different object does not really matter. Let's say same object. But here it will not be in equilibrium. Can you tell me why? What's the difference between it's the same 3 forces, the net force is 0, but in A, it is in equilibrium. In B, it is not in equilibrium. What happens is, this thing will not go anywhere. The center of mass of this, let me say the center of mass is here. It will be in the same place. It is not going anywhere. But the rest of the point will be spinning around this center of mass point. So there will be a rotation. Although there is no translation, we're not going, the center of mass will be remain in the same place. So the object is not going anywhere, but it is going to start rotating about this center of mass point. The reason is, if you look at this, all these forces are concurrent. They intersect at one common point. But here, the 3 forces are not concurrent. The word here, concurrent. So they don't cross at the single point. So that will make this object to rotate. It is clear if you look at this picture here on the right-hand side. Let's say you can do it on your own, put something on the table and you apply some horizontal forces. The vertical forces are balanced, the weight and the normal force. Say you apply a force of 10 Newton and you apply another force of 10 Newton, but this is up and this is down. What is the net force? 0. Net force is 0. So we expect this to be in equilibrium. However, in the second case, it is the same 2 forces. The net force is also 0 because we have here minus 10 and here plus 10. Net force is 0, but you know that that is not going to be in equilibrium. Same thing is going to happen. The forces are not concurrent. That will result in what we call a torque. So torque is not 0. Whatever it is, we will define it in a short while. Net force is 0, but the net torque is not 0 because they are not being concurrent. So that will be not in equilibrium. So that is easy to understand than this with just 2 forces. So we will now go to the next slide. So for an extended object, an object that has size which cannot be reduced to a point, we need to worry about where the force is applied. So that's why, when you don't have the forces concurrent, we are going to have no equilibrium. It's distracting. We are going to have no equilibrium. Right. So for an extended object, we have the rigid object model. Now you understand the meaning of the rigid, okay, compared to non-rigid. Like solids are usually a rigid object, okay. So liquid, gas, they are not rigid object. Even within solid, we can have an object which is not rigid, like a jelly. Okay, so it wobbles, right? So it is not considered as a rigid object. Technically, these two conditions has to be satisfied for something to be rigid. Say, take 2 points on the object, and if the distance between A and B, any 2 points, it has to remain the same over the time. It shouldn't change. But something like a rubber or jelly, it is not the case, right? It is going to shake, and the distance between any 2 points A, B is going to change with time. So liquid and fluid and gases, it is not going to be, they are not rigid object because it doesn't satisfy. But that alone is not enough. You can take the third point, C, and this triangle that is joining these 3 points, let me say alpha, this angle is beta, and this gamma. These 3 angles, choosing any 3 points, must remain the same over the time. So when these 2 conditions are satisfied, it is called a rigid object. Okay, so we don't have to worry too much about it. Roughly understand. Okay, what is a rigid object? So whatever we derive now, apply to rigid object. Okay, now we are going to introduce this concept, torque. You know about forces, right? If you have a non-zero net force, it will produce acceleration, meaning it will change the velocity. The moment you have a non-zero net force, or loosely we can say, a force will produce acceleration. Okay. But for rotational acceleration, what is my rotation? We can talk about a wheel is rotating at a rate of rotational velocity. You can say RPM, how many revolutions per minute. That is rotational velocity. If you want to change the rotational velocity, what we need is a torque. Torque is not something that comes from nowhere. It has to come from a force. Okay, we cannot define a torque without a force. Okay, we did not define it yet. We are going to, but it's not something out of nowhere. It is coming from a force, but it's not exactly the force. It is defined in terms of force. So any force going to have a torque on when it acts upon an extended object. So we'll see what this torque is. The best thing is to demonstrate this torque using this seesaw. I have a site here. Oops, let me go back. I'm going to open that. It's very easy to explain this torque using this simple seesaw. Seesaw, what is seesaw? Let me take the support out. It's just a plank, okay? Children play, they sit either side of the seesaw, they go up and down, that is seesaw. So now it is balanced. It's supported in the middle and it is balanced. So let me put some people on it, okay, some weights on it. So I support it now, then I will release the support. Now let's say I keep it here. From the center, it is 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, 6 meters away. And I keep it here. It's also on the right side, it is also 6 meters away. Now, do you think it will be balanced if I take the support out? Yes. Okay, because what happens here, these forces exerting what do you call a torque to rotate it. This is trying to rotate it counterclockwise. This is trying to rotate it clockwise about this pivot point, the support in the middle. But they are balanced. The torque is balanced. So the tendency of a force to rotate something is called torque. It's not the same as force. I will demonstrate it using this. If I take this out, you know what happened? This guy is applying a torque, something to rotate it, counterclockwise. So if I want to balance it, I have to keep it in the same place on the other side. So we have now balanced torque. The counterclockwise torque from the left guy will be balanced by the clockwise torque from the right guy. So now let me keep the support. Then I will take this out and put this 10 kilogram. You know what is going to happen, right? Because now the torques are not balanced. Because the force on the right-hand side is increased, so we expect the torque, the clockwise torque is going to increase, understood. So if you want to see, I can show you. Yes, as it suspected, you know, the clockwise torque is greater because the force is greater. Right, now I will take it out and I will keep it here. Same guy. What do you think will happen? Who is going to win? Which torque, the clockwise torque or counterclockwise torque? It will be balanced. Are you sure? I'm not so sure. I think the clockwise torque will win. Okay, how do I know that? Yeah. Yeah, the torque is going to depend on the distance to the pivot point, right? So let me count. 1, 2, 3, 4, 5, 6. Here it is only 2. I am going to predict, if I make the product, the weight multiplied by the distance is the torque. So this is 5 into 6 is 30, right? So how can I make this side also 30? Now what is it now? 10 into 2, 20. So if I bring it here, 10 into 3, 5 into 6. Now I am balancing the torque. So now you understand the torque is a property of the weight, the force, as well as the distance to the pivot point, the rotation point. So now, if what I said is correct, it is the product, they should be balanced. Yeah. Okay. Now you know how we can define the torque. Now let me go back to this. So this is the story. I mean, I have done this, so I can skip this. You can, if you want, you can look at it. But we have done a better job with our simulation. So now you are comfortable if I say that the torque is equal to, if you have a force which is perpendicular to that the distance that we draw, the r is what? R is the distance from the force, if the force is perpendicular, to where you want to take the torque. It's actually from where you want to take the torque, or the support point, the rotation axis, to where the force is applied. So that is what R, multiplied by F. Actually, if the F must be perpendicular. If it is not perpendicular, then you must take the perpendicular component of that force. So if you know the angle theta between this R and the force, perpendicular component will be F sine theta. So finally, we say the torque, we use the, okay, I should have said that, the symbol, this symbol for the torque, T-O-R-Q-U-E, torque. And the magnitude, it's a vector. Why is it a vector? We have direction, clockwise, counterclockwise. So we say counterclockwise is positive direction, clockwise is negative direction. Stick to that. The magnitude is simply equal to R, where R is the distance from where you want to take the torque, in other words, the pivot point or the rotation axis, to where the force is applied. And F is the magnitude of the force. Theta is the angle that is between the vector R and the vector F. Okay, the R, if I take it as a vector, drawn from where you want to take the torque to where the force is applied. So that is the direction of the R. And theta is the angle between the vector R and the vector F. So we can also say that if I combine these two together, it is nothing but the perpendicular force. So you can simply say the torque magnitude is equal to R multiplied by only the perpendicular component of the force. Perpendicular to what? Perpendicular to R. What about the unit? Force is in Newton. This is in meters. So the unit will be Newton meter. But we can give it in terms of the basic units because Newton is not the basic unit. Newton can be broken into kilogram from the Newton's second law, meter per second square, and meter. So that means in terms of the basic unit, it will be kilogram meter square. But nobody used that. We just say Newton meter. That's enough. Right. So here we have a bar which is fixed at this point, and a force is applied here, say F. And if someone asks you, get me the torque, the magnitude of the torque, it's very easy, right? R. What is R? It's a vector actually, but here the magnitude of the vector. R is simply the line that you draw from the pivot point or where you want to take the torque to where the force is applied. Where is the force applied? Here. The force is applied here. So this is your R multiplied by perpendicular component of the force. Perpendicular to what? Perpendicular to the vector R. So it will be the rod here. So you need to take that. If you know the angle between the R and F is theta, okay, this is the angle theta, then perpendicular component will be F sine theta. Okay, so for this you can substitute F sine theta. Right, that is the magnitude. What about the direction? Is it going to be, is the guy going to rotate it clockwise about the pivot point or counterclockwise about the pivot? Counterclockwise, okay, counterclockwise, okay. So you put positive. So counterclockwise is our direction. It's not actually a direction, but we are going to say it is positive direction, and clockwise as negative direction. So what happens, this is very clear. Now suppose you want to open a door, say this is a door, and you pull like this, is it going to open? If theta is 0, if you apply the force with theta equal to 0, can you rotate it? No way. So we have only parallel component of no use in the torque. So it must be greater than theta equal to 0. Maximum effect is when theta is equal to 90 because sine 90 is 1. Anything between 0 and 90 will be less than 1. So the maximum effect for turning will be when you apply the force perpendicular to the R. Right, now we have some question. The following slide shows different configuration where a force is applied to a uniform bar that can rotate freely around an axis. The dots represent the axis of rotation and the force arrows all have the same length. Which of these configuration will produce the greatest torque? Okay, that's, I'll explain the question again, but probably, I went fast. No problem. So we have 5 configuration, and the rotation axis is here. In this case, it is here. In this case, again in the middle. Here in another corner, the same corner. And we are applying a force F, which the same magnitude. Okay, in all configuration, say let's say it's 10 Newton. It is always 10 Newton, but different orientation, different direction. So which is the greatest torque of this A, B, C, D, E? The last one, okay? So that's a very easy one, but let's go slowly, okay? Now, will it be very accurate? So tell me what is the torque here in A, in this? Y? Yeah, R is 0, okay? So good, all right? The reason is R is 0. What is R? From the pivot point to where the force is applied. It is the same place. So the length is 0. So R is 0. That's right. What about this? R is not 0. R this be this, right? From the pivot point where the force is, this will be the R, and perpendicular component will be this much. Okay, so we know roughly how much it is. Here, R will be greater, perpendicular component is almost the same, maybe same, that's the same. So this is greater than that, no problem, but we have to check everything. Here R is this much, and perpendicular component is the whole thing. This is the whole thing perpendicular, so the perpendicular component is greater there. But however, R is small, so we really don't know, this is greater than that, about this, I don't know unless we give some values, right? But let's go to this. We need only the greatest. Obviously, this is big and this is the whole thing. So E is the greatest. That's easy to answer. Right. Now we have a question with numbers. So let me go to the picture, okay? Then I will explain. So there is a bar and it is rotating about this point. So he is asking to get the torque about this point. That is very important, okay? The torque, you have to tell me about which point. Otherwise, that question has no meaning. Someone asks, what is the torque? The question is not complete. You have to tell me about which point. So because the torque about this point and say another point Q, there will be two different answers. The torque about P for the same force will be different from torque about Q by the same force. Okay, so this is very important. So one has to mention about this, which point. So say now this is point. He is asking what is the torque. He is given the R is given to us. The length of the rod will be the R, right? Because from here to where the force is applied. So R is given to us. I don't remember what the value is. Okay, 1.736. Just remember that. So 1.7 meters, and the force is 36. So we have everything we need to answer the question, what is the torque? Torque will be, magnitude of the torque will be R into F perpendicular. So F perpendicular will be, this is the total force, so the perpendicular will be this much. So you can just substitute the values R, F sine theta and get the answer. R will be 1.7 and theta will be this angle, the angle given to us, that will be the same. So that is the angle between this. So the perpendicular component will be the same theta, which is equal to 36, right? You get the answer. What about the direction? Is it going to rotate clockwise or counterclockwise? Clockwise, right? It's obvious. You just imagine you press this point and that is the only force, so it is going to rotate clockwise. So you put it's not because it is down or up. No, you should really see for yourself, visualize, and figure out whether it is going to turn clockwise or counterclockwise. Yeah, I have to make another point now. That is, good, you understand this R in, correct. I can do one thing. I can join this with this and write it in this way. F multiplied by R sine theta. I'm writing the same thing, right? It is correct. The magnitude will be, instead of saying R F sine theta, I just rearrange the thing. I can say F R sine theta. Now, what is this R sine theta? Does it have a meaning? Yes. So we apply the force like that. And this is R sine theta. If this is theta, that means this is R sine theta. So I can say the torque can also be put forward as force, entire force, not the perpendicular force, entire force multiplied by the perpendicular distance of that force to the rotation axis. Right? So it's another way of getting the magnitude of the torque. So if I summarize everything, the torque, actually the magnitude, you can say this, or you can say the torque is equal to this, which is the perpendicular distance of the force to the pivot point. Sometimes in certain questions, it's easier to find the perpendicular distance than the perpendicular component of the force. So that becomes useful in that case. All right, now there is a mistake. It's clockwise, right? Yeah, there's a print typo there. I have to correct it. So we saw that it will be clockwise, not counterclockwise. Right, now talk as a vector. You know, R is a vector, F is a vector. Both of them are vectors. So I can say torque is a vector and it is given by the vector product of these two vectors. The magnitude of this vector, by definition, R magnitude, F magnitude, sine of the angle between R and F. So we get exact same formula. That is how we define the vector product of two vectors. Okay. So it's a bit some advanced math, where some technique, but you don't have to worry too much about it, but at least know this. Okay. So you can define the torque as the vector product of the two vectors R and F. So by definition, how do you get the magnitude of this? Simply first magnitude of the first vector multiplied by magnitude of the second vector multiplied by sine of the angle between the two vectors. So we get exact the same formula again, but this also tells us how to get the direction. So that's the point that is more important. How do you get the direction of these two vector product? We use a technique called right hand rule. So let me show that here. So here we have a plane, say like this. So in this plane, we have two vectors. The R, the red one, let's say R. So I use this pen, this blue pen, as R, and I will use this whiteboard pen as F. So R is like that, F is like that, right? Can you, like this? Am I roughly okay? So this is the plane. I am showing it like that. So this is the value R, and this is the F. Can you visualize that picture? All right. So I'm going to keep it like that now. So what do you have to do now? This is the tip. No, this is the tail of the vector R, and this is the tail of the vector F. You need to bring them tail to tail, okay, without changing the orientation. So this is R and this is F. But the head is touching the tail, right? That's not good. Either you move the R so the tails are together, or you move the F so the tails are together. Then you know what is the angle. The angle is this. After bringing tail to tail only, you know the angle, the smaller angle between them. Now, you keep like that, then what you do, you take your right hand, not left hand. That's why it is called the right hand rule. And stretch your fingers in the direction of R. You can keep it like this, like this, like this. You have choice, right? But keep it so that you can bend or curl your fingers towards F. If you keep like this, can you curl it towards? You can, but it is through a long angle, right? If you keep like this, can you curl? No way, right? Because this is here. So you must keep it like that. This choice is out because you have to curl through a big angle. So you keep it like that, and you can curl, and look at the thumb. Thumb is pointing up. So that is the direction of the torque. Thumb is pointing up. So that's the direction of the curve. Now suppose the force is like this, not like this, like this. Then R will be, F will be to the right of R. Then if you keep it like this, can you curl? It is a long angle. So you have to keep like this. If you keep it like this, it's no way anyway. So you have to keep like this. Then you can curl. The thumb is pointing down. So I hope this picture explains everything. So although I showed it like that. Okay, now, when you look from above, what direction will it rotate? Clockwise or counterclockwise? Counterclockwise. So counterclockwise is up, so positive. Clockwise is down, therefore negative. So even if you don't follow this, you don't have to worry too much about this rule, because all you need is whether it is going to turn clockwise or whether it is going to turn counterclockwise. But strictly speaking, these are not direction, right? It's just keep going round. Can you say it's a direction? No, that's why we need a proper direction. So by applying the right hand rule, we give them a proper direction. So counterclockwise, if you are looking at the board, screen, counterclockwise will be out of the board. Clockwise will be into the board. So out of the board is positive, into the board is negative. So there is a little bit more there, one more slide. This is the R and this is the F. And this RF sine theta is nothing but the area of the parallelogram formed by the vector R and F. Okay. You don't have to remember that, but just remember RF sine theta is the magnitude. In other words, it is also the area of the parallelogram formed by R and F, and the direction will be coming from applying the right hand rule. Right. So there are a lot of words here, but I will explain very quickly. What he is asking is, the torque is given by R cross F, vector multiplication of R and the vector F. Suppose I wrote it like this, F multiplied by R. Is it correct? No. Okay, vector multiplication, the order is important, because when you put like this, R cross F, we say cross, okay, then you understand it's a vector product. R cross F, you put your fingers, stretch your fingers along the first vector, not along the second vector. So if you use the second one as the correct equation, then you have to put the fingers along the vector F, not along the vector R. Then the direction will be opposite. So you don't use that. That is wrong. The order is important. So the torque is equal to R multiplied by the vector multiplication by F. So that's all this question is about. Okay, so right now we also have to add the torque. Okay, because let me give an example. It's a very nice example. Let's say you have a bar and it is pivoted here. Somebody comes, he wants to rotate it counterclockwise. Okay, let's say he wants to rotate it counterclockwise. So he apply a force like that. Do you think it will be rotated counterclockwise? This is the pivot point. Say 10 Newton, and say he at a distance of 5 meters away, he want to, okay, it will rotate counterclockwise, right? Okay, so it's a positive torque. Good. And he wants help. Okay, maybe his force is not big enough. You ask someone else, okay, please come and help me, give me some help. So he comes and he gives a force. Okay, I'll help you to rotate counterclockwise, and he apply a force like this. Let's say at a distance of say 7 meters, and he apply a force of 2 Newton. Okay, is he really helping? No, because his torque is clockwise, but I want to rotate it counterclockwise. So, of course, what will happen? Will it rotate counterclockwise or clockwise? His torque is 50, plus 50, and the other guy's torque is minus 14. So the net torque is 50 minus 14. Still it is positive, but instead of helping him, he is actually not helping. He is actually working in the opposite direction. So he has reduced the torque. So we need to, when you want to add torque, you have to keep that in mind, because if you say the total torque is equal to 50 plus 14, it is wrong. You have to put the correct sign, then only you will get the correct net torque. So net torque means you add all the torque, but you have to keep in mind to put the signs. It's a vector. It has direction. Only two direction because you are talking about one-dimensional fixed axis rotation. You can treat it as one-dimensional thing. So you have only two direction, clockwise, counterclockwise. Right. So now we are ready to do a question. Find the net torque. A bar is acted upon by three forces, F1, F2, F3. So you have to find the torque from 1 and the torque from the force 2 and the torque from force 3 about, that is important, around the pivot point. I need the torque about the point P. Okay, if you don't mention that, you cannot answer the question. One should mention around which point, about this point. So here he's telling about P. So that's not difficult, right? So torque 1 will be what? Can someone help me? R is this much, right? Which is 2 meters. So you'll put 2. And F is 12. But actually I want the perpendicular component. That will be 12 because this angle is 60 with the R. So perpendicular will be sine 60. But I'm not quite finished. Why? The sign. This is very important, okay? But now you know how to get it very quickly. Don't look at the direction of the force. It's not the direction of the force. You have to see about this point. Is this the only force? Forget about the other forces. If this is the only force, which direction it is going to turn? Clockwise. So put a negative. So that's how you get the sign. Now quickly tell me what about F2 and F3? Are they clockwise or counterclockwise? Counterclockwise, okay? Not because it's going up, okay? Suppose I told you take the torque about the point Q. What about F3 now? About point Q, the same force is going to rotate clockwise or counterclockwise? Clockwise. So this is very important. It's not because the force is upward. You should look at the point where you want to take the torque. Then according to that, you will either get it clockwise or counterclockwise. So, you know, now I don't want to go through all this. So you can get the rest of it. So it is solved in the next slide. I can show you. So this is both of them are F2 and F3, and that is positive. This is the torque from F1. So add them with the correct sign and the correct substitution. Then finally, it turned out to be a positive torque. So the net torque is a positive one. Yeah, let me continue. I'll take the attendance at the end, okay? All right. So this one, I think probably you know better than me. Anyway, let me check. Do you know the name of this? I know, you better tell. Okay. Scapula. All right, good. And this joint? No, what is that? This is the forearm, right? And this bone, humerus. This one, radius. This one, ulna. And this is the bicep. This is the tricep. So as I mentioned before, actually the tricep is joining the ulna, right? The tricep is connected to the ulna. Am I right? Yeah, in the forearm. And the bicep is connected to the radius. So these are the muscles like a rope. They can only pull. Can you push with the rope? No. Muscle also, you know, it's a tendon. It is just a pulling, pushing thing. Pulling, can only pull. So if you want to do this, what do you call that? Flexion. What do you call this? Extension, yeah. If you want to flex your arm, can you use the tricep for flexing? No. Tricep is connected to that, but it can only pull, so it can only extend. So that's why you need these two pair. So this one, the point here is that I want to make is this is the pivot point, right? And R is only this much small. Even this also, the R is very small. We want to rotate this arm, okay? When you flex, it is counterclockwise. When you extend, looking from your point of view, this is counterclockwise, right? And this is clockwise. You need these two torque. The torque is going to be small because R is small, right? Because torque is R. Because if we had the muscle connecting here, it will be advantageous, right? We don't need to apply much force. But but there are other disadvantages. There are some advantage by having this, but anyway, we have no choice. This R is small. So suppose he is going to lift a big weight, he has to apply a big force. The muscle force going to be greater. So that's we can think of as an advantage, disadvantage. Same thing with the tricep. Okay, when you go to extend, but that we have a help. Who is the helper? Gravity. Because you don't have to do anything. The tricep can relax. It will come down by itself because of the torque from the weight you have, the gravity. Okay, so but flexing, you're going to work against the gravity. So anyway, there are certain things that are related to medicine. So I'm just going to read from this slide. So you understand why we need a large, since tendons connecting the muscles to the bones are usually attached close to the joint, large forces are needed to achieve locomotion and equilibrium. You know why? Because R is small. So we have to compensate it by having a big F. These large forces are of interest in kinesiology and medicine because joints have a relatively high likelihood of failure during their lifetime, not only as a result of injury, okay, the tendons become weak and cannot exert much force, but also as a result of degeneration, arthritis, the joint problem. Right, now we come to equilibrium. Equilibrium for a rigid object. We know about this already. The condition for equilibrium is net force has to be zero, otherwise there will be acceleration. Acceleration means velocity is changing. Velocity is constant mean equilibrium. Velocity is changing mean no equilibrium. So this condition is called the condition for translational equilibrium. But we saw that at the beginning, the first slide itself, that's not enough. Because we can have the net force zero, but if the forces are not concurrent, they are going to be a torque. So that requires a second condition. The net torque also has to be zero. And we call that condition as the condition for rotational. You should know these names, okay? What is rotational equilibrium? The condition is net torque is equal to zero. What is translational equilibrium? The condition is net force is equal to zero. The next slide shows 5 locations of fulcrum along a red bar upon which 5 forces of any magnitude act. Which of the 5 cases cannot be in rotational equilibrium? All right, this is a very nice question. Okay, we need to spend some time. Okay, if you understand this question, then you kind of mastered the idea of the torque. Let me explain this question again. So we have 5 configurations, A, B, C, D, E. A bar is supported in different places. Here we call the fulcrum where it is supported. The fulcrum is here, or the rotation point is here, or pivot point is here. Here it is there, in different places. And we apply 5 forces. These 5 forces are applied in all of them with the same location, at the same location. You can see the picture, right? They are all applied in the same location throughout this. And same orientation, direction in all 5. Same location, same orientation. You are given the freedom of changing the size of the force independently. You can reduce this, increase this, but cannot change the location, cannot change the direction. You can change the size, but not to 0. It cannot be 0, but you can change the size, keeping the same location and the same orientation. Okay, now I think you got the details. The question is what? Question is, some of these A, B, C, D, E, you can have rotational equilibrium. Some of them we cannot have rotational equilibrium. Which one that you cannot have rotational equilibrium? That is a question. Okay, I'm going to go to A and analyze A with you. Then you will get the idea. Okay, let me analyze A with you. So this is, let me 1, this is 2, this is 3, this is 4. I'm going to label them so I can refer to them by their name. Look at the first one. What is the torque? Okay, very good. Okay, the torque is 0. Why? R is 0, right? Okay, number 2. What is the torque, positive or negative? Clockwise, right? About the fulcrum. About the fulcrum, you have to keep that in mind. So the torque from this guy is 0. Torque from this guy is positive. Number 3. Sorry. Negative. Okay, torque from 3 is positive. Torque from 4 is positive. Torque from 5 is 0. Why is it 0? Is it R0? No perpendicular component. In other words, theta is equal to 0. Sine 0 is 0. Another way of looking at it. Okay. So we have here some positive, some negative. At least one positive and at least one negative. That's the thing that you have to get into your mind. We have the freedom of varying the magnitude of the force. So we can do that so that we get equal positive value and equal negative value. We will have rotational equilibrium. So he is out. He is out. We'll do the second one. We have to go a little faster now. Okay. This guy is out because this can be made to rotational equilibrium. We have to pick the one which cannot be made to rotational equilibrium. Okay, we'll go fast. Tell me this, positive or negative or 0? Positive. This one, negative. This one, positive. This one, positive. This one, 0. Do we have at least one negative and at least one positive? Yes, he is also out. That's how you get it, okay? Okay, let me go to the E. Are you sure E is the one? Okay, let me check E. Right, let me start with this. This is the fulcrum. The fulcrum is moving. You have to keep track of that. So this one is positive. This one is positive. This one is. So this guy is going to be positive. This guy is positive. This will be negative because you're going to go like that. Okay, it's negative. So this is out. C. Sorry about that. Okay, right. What about C? Let's go fast. This is a fulcrum, right? You have a doubt? Is it okay? Am I okay there? Yeah. All right. This one, 0. This one, 0. This one is positive. This one is positive. This one is 0. C. All right. So we don't have any negative. No matter what you do, you have the freedom of changing the size of the force, but not to 0. That